All right, hello. My purpose of this short video, hopefully short video, is to show you how to complete a series solution differential equation problem. And let's go to share screen. Now I'm going to go through a lot of the basics here. And the equation I want to work on is, let's say, suppose we have y double prime minus x plus 1 y prime plus x squared y equals 0. Now, okay, you moved it over a little bit. Just try to move this a little bit, a little higher. All right, there we go. Now, it should be okay. A little bit of glare, but I think you can still see it. Focus. All right, now, the idea here, what the idea behind this is, first of all, if you notice the coefficient functions in front of the y prime and in front of the y are in fact analytic. In fact, they're polynomials, so you don't have to worry about them having a series solution. So you're guaranteed to have a series solution. Now, what is a series solution? A series solution is an expression of y as a power function plus a2x squared plus a3x cubed, etc. Or in summation form, we start summing at k equals 0 to infinity of a k x to the k. So this, you can think of this as an infinite polynomial, if you will. And as a power series on its open interval of absolute convergence, that's from calculus, its open interval of absolute convergence, y can be differentiated term by term. Now, we're assuming the solution looks like this. And what we want to do is, our goal is to solve for the coefficients, etc. Now, sometimes you can get a solution that is easy to get, where it's clear what they are, and sometimes its formulas aren't really nice, and you just have to settle for getting a few of the coefficients. But the more of these, now if we know them all, we know the entire function. Often what we're trying to do is we're trying to get at least the first few of them. Okay? So now, if an idea here, and this is a procedure. So I'll give you the steps. Procedure. 1, you differentiate our proposed solution. And you do it as many times as there are derivatives here. Here it will be twice, 2 times as we have y double prime. That's our highest order. That's the first thing we do. Second, plug into the differential equation. And 3, we do algebra. G to make the left-hand side equal the right side. Now here, the right side is 0, so it's going to be relatively easy. If the right side were a function, you get the power series for that function, and then you equate the coefficients. And you do 3 by gathering the like terms. Okay, that's how you do it. All right, so without further ado, let's go ahead and do this. So remember, these are the steps. That's how you do it. I'll move it over here. Those are the steps. So let's start off. We have our y is this. Now remember, this is a series representation of that. Now y can be differentiated like a polynomial. So let's do this compactly. You take k, a to the k, x to the k minus 1. Now, you can still start at k equals 0, because you might say, well, wait a second, don't I have a k minus 1 here? And yeah, you do, but the coefficient, it starts at 0. So this y prime, if you wrote this out long way, it would be 0 plus a1 plus 2a2x plus 3a3x squared. See, each one of these terms you get by differentiating. You differentiate a naught, you get 0. You differentiate a1x, you get a1. You differentiate a2x squared, you get 2a2. You differentiate that, 3 comes down, 3a3x squared, and so forth, just like calculus. Now y double prime is going to be, well, you're differentiating that, plus 3 times 2a3x. Then we get our next term, there would be an x cubed here, 4 times 3, a4, x squared, and so forth. Or in summation notation, we get a k minus 1, a k, x to the k minus 2. Now notice, you might be saying, well, wait a second, do we get negative powers? Well, no, if we plug in 0 here, that's a 0. You plug in 1, that's a 0. So the first non-zero power you get is when you plug in k equal 2. And that's the constant power right here. So that's what we did. We've done step 1. We've differentiated our proposed solution. Okay. Step 2 is we now need to plug this in to our differential equation. So let's just do that. And I'm going to do it in a way where you kind of, where you have the terms right over each other. Notice this starts at 0. So you can probably, to get this in, well, let's just do it. So we plug this in. K minus 1, x to the k minus 2. Remember, this starts at this. That's going to be a y double prime. Our next thing is going to be a minus x plus 1 y prime, right? Because we got to plug this into here. Well, this is x plus 1 negative sum k, a k, x to the k minus 1. That's going to be starting at 0 infinity. And then we get x squared times the original function. That's going to be our x squared y, right? Now, let's go ahead and try to write these out in a way where we can do like powers. Now, the idea here is that all the x to the 0 powers, well, let's just do one more bit of algebra, then we'll do this. The first one starts 0 to infinity, k minus 1, x to the k minus 2. Remember, that's our y double prime. Now let's do this one in 2 parts. So if you multiply this by x, we get 0 to infinity, k, a k, x to the k plus minus 1 times x, which is just k. And then we subtract when we multiply by 1. That's minus x plus 1 y prime. And then we have this, 0 to infinity, ak, x to the k plus 2. Now notice we're starting at 2 here. Now the idea here is we now wish to do, we plug this into the differential equation. Now what we want to do is we want to gather the like terms. So this part is done. Now let's gather this into like terms. And here's where we have to think about this a little bit. I realize I neglected something here. I forgot my AK here. That's important. This is AK, x to the k minus 2. So this is an AK here. I forgot that part. Now we need to figure out, we need to get the like powers. And remember, this actually, the first and this is where I think it helps to write this out so we can get our formula here. This is strictly correct, but remember we have a 0, 0. And let's go ahead and write these out a little bit long way. So I'm going to move this over here. And let's look at our y double prime written sort of the long way so we can gather this. There is sort of a slick way of doing this, but I think this will help us. So notice if we plug in 0 here, we get a 0. You plug in 1, you get another 0. The first one that isn't 0 is 2. So y double prime is going to be a2 x to the 0 plus a3. Oops. Okay. You plug in a 3. That's a 3 times 2. Let's see. Well, let's go back here. Okay, k equals 2. This k equals 1. That's a 0. K equals 2. I get a 2 a2 x to the 0. The next one, you plug in a 3. 3 times 2. X to the first power. Let's go a couple more. Okay, 4 times 3. A4 x squared plus, let's do one more. 5 times 4. A5 x cubed. Now this goes on and on and on and on, right? This continues on forevermore. Now, the next thing we have is let's go to this one here. Subtract. I'm subtracting this term right here, and again I'm going to start at a k equals 0, you get a 0. A k equal 1, we get a positive, we get a negative. A1 minus 2a2 x minus 3a3 x squared minus 4a4 x cubed. Then I have this term to do. I haven't done that one yet. Now that starts at 0. So we have a a1x minus 2a2. Oh, here's my k here. X squared minus 3a3 x cubed, so forth, right? So we got these nice and aligned. So we've done this one, we've done that one. Now we got to do this one. And notice this one starts at x squared. So this is going to be a a0 x squared plus a1 x cubed and so forth. Now what we do is, now that we have all these terms, we now consolidate them. So see if we can get a pattern. We get 2a2 minus a1 plus this next one here, 3 times 2, a cubed, a3 minus 2a2 minus a1, x. Now we get the next one. So we get 4 times 3, a4, minus 3a3, minus 2a2, plus a naught, x squared, and let's do one more. We get 5 times 4, a3 minus 4a4 minus 3a3 plus a1, x cubed. Now the general pattern, I think you might be able to discern it out of this right here. So the general recursion relation, well, let's see what we have here. This is going to be k plus 2, k plus 1. Let's see here. Well, let's take a look here. We have to determine what we want our k to be. So I'm gonna, okay, let's go ahead and call that the k. So that's going to be minus k a k. Now this has 1 power less, so it's minus k minus 1. Well, let's see. Let's look at the general pattern here. The general pattern is that we have a minus, let's call that k plus 1, a k plus 1. I'm using that as a power. That's that. Plus, now we have k plus 2, k plus 1, minus k, ak. Then we have this, plus a k minus 2. That's times x to the k. So this is our general relation here. This will tell us every single coefficient. So this is the general, and I got this from this pattern. You see the 4 is 1 more than that. This is 5 times 4, which is 1 more than that. So this is 2 less than that. That's the general pattern. Okay. Now let's start solving. So now when we start to solve, it's going to be very, very important that we let that the left-hand side, which is all these, has to equal the right-hand side, which is 0. So to make this 0 for all x, to make this equal to 0 all x, we get 2a2 minus a1 is 0. Or what this is the same thing as saying is a2 is 1/2 a1. We got that. The next thing says 6a3 minus 2a2 minus a1 is 0. 6a3 is equal to 2a2 plus a1. But then a1 is just 1/2, a2 is just 1/2 a1. So it's 6a3 is equal to 2 times a1. It's going to equal 2a1. So a3 is equal to 2 divided by 6 is 1/3 a1. Okay? So we've resolved this. Now the next one is where a0 actually starts to come in a little bit. We have 12a4 is equal to 3a3 plus 2a2 minus a0. Just going backwards here. Now notice a0 has not been resolved. these two half. This is 1/3 A1, so 3 times 1/3 is you get an A1. 2 times that is another A1. So this is 2A1 minus A naught. So A4 is equal to this divided by 12. Okay, that's our A4. Now let's go ahead and try to do I'm going to keep this. And then let's try to do the general thing. And again, it's a lot of algebra, but we're solving for these coefficients here. So what we have is minus k plus 1, a k plus 1 is equal to minus, well, this is going to be k plus 2. Well, let's just do the minus by reversing this. So this is going to be k minus k plus 2, k plus 1, minus a to the k minus 2. And that's what this negative 1 is equal to. So then you divide it, and you get a k plus 1 is equal to, now I'm going to switch the order again. And this is your general recursion. This is, of course, all multiplied by AK. So this is your general recursion relation. Now, what does this all mean? This looks like a lot of just writing it down. Well, let's go ahead and finish this up. Remember, our original solution was y is equal to a naught plus a1 x plus a2 x squared plus a3 x cubed, etc. Well, now we have not resolved a naught. A1 we have not resolved. And that's, in general, we're going to get 2 of these. Now your A2 we've already resolved. That's going to be 1/2 A1 x squared. Your A3 we said was 1/3 A1. Your A4 we said was this. And then we can go here. And then your A5, we can use this right here. Well, we can resolve this a little bit further, but let's just stick with our first 4 terms. But basically, we get the rest of the terms by plugging into here. So this would be A5. This would use k equal 4. So that would be A4. 4 plus 2 is 6 times 5 minus 4 divided by 5 minus 1/5 A3. And we've already solved for A3 and A4. Well, which we have right here. So what does this tell us? Well, our solution looks like this. I'm going to just use this to write this down. Let's look at our A naught. And notice, let's look at every term that has A1. So we have an A naught. Let's look at our A naught. So we have an A naught. Where's the next time the A naught appears? Right here. So it's minus A naught over 12 x to the 4th, and here's some other terms. So that's going to be an A naught, 1 minus 1/12 x to the 4th. And, you could solve the rest of the way. Plus, let's look at our A1. We have an A1. What do we have here? We have an x. We have another A1. plus 1/2 x squared. We have a third right here. Then we have a 6 right here. And so forth. So you see, our solution is written as a sum of two power series. One involving this initial constant and one involving this initial constant. Now, you resolve these by figuring out what the value at 0 is and what the value at 1 is. So let's say, if y of 0 was equal to, let's say, y naught, well, that would be this right here. Now y prime of 0, well, you differentiate this. Well, this would be a 4 over 12x cubed. Then you plug in a 0, you get a 0. You differentiate this, you get an a1. So this would be a y, this would be y1. This happens to be a naught, and this happens to be a1. Right? So that's how you find a series solution for a differential equation. There's a lot of algebra here, but just remember, the whole thing is that you're assuming that there's a series, and you don't know what the constants are. You plug the series into the differential equation. You do algebra to gather all the like terms, all the like powers of x, and you try to make the left-hand side equal to the right-hand side. And that's how it goes. Thanks for watching.